Hello and welcome to this presentation. My name is Keith Felton and I'm the Product Marketing Manager for Mentor's IC Packaging Solutions. During the next 20 minutes, I'm going to talk about what advanced IC packaging is as a technology, its design and verifications needs, the resulting challenges, and how Mentor is addressing those challenges and needs. I will start with an overview of what Mentor calls high-density advanced packaging, the broad challenges it brings, and how adopting a virtual package model is key in addressing such challenges. We will then take a deeper look at the verification challenges and what approaches can be used to address them. We'll then conclude by looking at a real-world customer example and wrap up with a summary of what you should have learned from this session today. Monolithic SoC design is no longer the path for achieving the functionality many applications demand. It's now only really viable for ultra-high performance applications where the cost, risk and challenges of doing advanced node design is not a primary factor. Instead of the challenge of integrating functional IP blocks all at the same process node, there's now a trend for disaggregating the once monolithic device into a collection of node-optimized heterogeneous or homogeneous IP chips or chiplets, which are typically interconnected together on some form of high-performance interposer as part of an advanced IC package. Such integration offers a path to enhanced device functionality, faster time to market, and silicon yield resiliency. Multiple integration technology platforms have emerged that allow for cost, size, performance, and power optimizations that satisfy the need of a broad set of market segments, including mobile computing, automotive, high-performance computing, augmented reality and virtual reality, artificial intelligence, Internet of Things, medical, aerospace, and of course even 5G. Mentor created the term HDAP to categorize advanced packaging technologies that we see as disruptive to traditional tools, methodologies, and in general need a new approach to the planning, design, verification, and sign-off methodology. Of the four categories, fan-out wafer-level packaging is probably the most well-known thanks to Apple and TSMC. TSMC created their INFO, known as integrated fan-out process, that was adopted by Apple for their iPhone A10 processor way back in 2016. And has been Apple's iPhone processor package platform ever since. As you can see, HDAP has multiple types, each providing advantages and benefits for specific applications and market segments. The real strength of HDAP packaging is its heterogeneous integration capabilities, where devices of different technology nodes can be integrated together, providing the performance, size, and power consumption and cost requirements that multiple markets demand that in the past could only be achieved using a monolithic single device approach. But such advanced IC packages also come with a number of challenges, many of which are new to IC packaging. The first is bringing all the elements together into a single accurate design model that can be used to drive downstream design and verification. As part of this is the need to construct a top-level or system netlist so that connectivity can be managed and verified during design and final verification. Once implementation of the various levels of substrate has been completed, then the task of verification can begin. Typically, you start with fabrication DRC of each substrate's metal layers, followed by package assembly verification, both at the logical and physical levels. The first step is to construct a model of the entire package assembly. It provides a single moment of truth, or a blueprint, that drives all level of implementation, verification, analysis and manufacturing. It also provides the golden system level connectivity netlist that will be used during verification. Development of the device's 3D assembly floor plan allows you to optimize the assembly connectivity across the entire package design, which lets you look at routability, interface planning, signal integrity and power delivery. It also drives static timing analysis, multi-physics verification and validation of the entire assembled device once design has been implemented. Mentor's solution for advanced IC package design assembly model construction is the product Xpedition Substrate Integrator. It has a wide range of supported input formats that provide maximum flexibility and ensures data integrity. It allows you to construct a hierarchical model that will then drive all levels of design implementation, verification, and analysis. Xpedition Substrate Integrator does more than just build a dynamic digital twin model of the complete package assembly. It allows the designer to optimize the connectivity on and between the different levels of substrate hierarchy to meet whatever goals of interconnect performance and routability they may have. Xpedition Substrate Integrator was designed to handle the largest of package design assemblies, typically seen in 2.5D and 3D applications, where commonly 250,000 pins or more exist. Just imagine trying to plan that level of package assembly using traditional spreadsheets or graphical schematics, a very challenging process. What makes this challenging is, of course, different databases for each level of the package hierarchy, different manufacturing processes, and of course, even different design tools that are involved in their formats, etc. But the basic needs of heterogeneous planning includes being able to capture and define the assembly stack and device relationships, being able to plan and prototype the connectivity across the different substrate boundaries, typically focused on the high-performance interfaces, and then communication of the design intent to the other implementation tools that are part of the process. The driver for design can vary. It could be a die-down driven design where the die bump assignments actually drive the package BGA assignments. Or it could be a PCB up driven design where a new IC package must be made to be compatible with an existing PCB systems design and its fixed BGA footprint. There is no right or wrong method. Each one is dependent on the application, and the planning process must accommodate that. Investing in cross-substrate planning during the early stages of design can greatly improve predictability during implementation by finding and fixing cross-substrate issues before they become late-stage design surprises. An early system perspective with cross-substrate visibility improves communication and coordination by providing immediate feedback to decisions typically made on an individual substrate implementation basis. A simple example would be optimizing the package ball pad assignments solely in the context of the dies that creates an overly complex PCB netlist, resulting in extra trace length or vias, or worst case, extra layers that add cost at the board level. By incorporating the critical areas of the board during the actual planning and optimization process, as seen here, enables you to make the trade-offs between complexity of routing at the different substrate levels and balancing the overall challenge across the multiple levels of substrate involved. One thing HDAP demands is extensive verification at multiple levels, not limited to verification of just individual die and substrates, but the complete assembly of the package. Such verification includes LVS, or commonly known as layout versus schematic, where system-level connectivity of the completed substrate assembly is checked back against the virtual model which provided the original golden reference netlist. Then there is something Mentor calls LVL, or layout versus layout. Here the actual as fabricated data is assembled using the virtual model as the blueprint. LVL allows for alignment checking of die, substrates, and other component interfaces which may have been compromised due to fabrication process impacts such as scaling. The data flow for Mentor's HDAP solution that comprises of Xpedition Substrate Integrator and Calibre 3D Stack. The individual source design elements are integrated and assembled as a heterogeneous system within Xpedition Substrate Integrator. This model is then directly driven into Calibre 3D Stack, where DRC and complete package assembly verification can be conducted using assembly design kits or process design kits provided by the manufacturing foundry or OSAT. Such a verification solution provides extensive and comprehensive capabilities across every level of the package assembly. By using the actual planned manufacturing data as opposed to the design tool's native database, you ensure that any post-processing errors are not introduced. And you're going to find out that most foundries and OSATs that offer advanced IC packaging technologies will require that your design is signed off using Calibre and their supplied assembly design kits. Calibre 3D Stack is directly integrated with the Xpedition IC packaging design tools. Any fabrication issues identified by Calibre, that's the right-hand screen image, are immediately highlighted in the design tool, Xpedition, that's the left-hand screen image, so immediately corrective action can take place without delay. So let's look at a real customer example. Here is eSilicon, recently acquired by Imphi. They turned to Mentor and used our solution that you saw here for the complete package verification of one of their complex 2.5D designs. Using our methodology and solution, it highlighted a number of connectivity issues that they were not aware of, and if they were left unaddressed, would have led to a significant design spin and corresponding manufacturing delays at the foundry. And this will, of course, impact significantly the project costs. What have we learned during this presentation? Well, first, I think everybody knows that every chip that's ever designed must be packaged. And high-density advanced packaging is a rapidly expanding technology that leverages heterogeneous multi-chip integration to deliver the performance, functional density, and cost targets that multiple market segments are now demanding. Mentor's Xpedition and Calibre technologies provide a proven path to HDAP design, comprehensive verification, and of course, foundry and OSAT sign-off. Thank you for your attention today. I hope you found this material educational. If you have need for further discussions, such as a discovery meeting or a process assessment, then Mentor's local representatives can make such arrangements at your convenience. Again, thank you very much for your time. Have a great day.